Last time I mentioned to you the levee breaks in New Orleans, and what I brought here was a photograph. I find this the most interesting photograph of the levee breaks. Let me put that there. So I described this to you in words last time about the levees being this reinforced concrete and how they broke. You see, these things aren't bent or curved. They just broke there. What actually happened was they were dug deep into the ground. As the water pressure built up, the ground began to give way, and this thing started buckling out like that, started being pushed out. When you take something that's straight and push it out, it tends to break, and it breaks along the expansion joints. So there are lots of things that could have been done. The fundamental problem is you never know where to spend your money, and a lot of money that could have been spent on this wasn't. It was spent on other things which didn't happen. So let's see. Should I give a quiz today? No quiz today. Sorry. I know many of you were counting on that. Gravity. Odd thing. I mean, the first thing to ask is, I mean, you know the old story that gravity is the tendency of things to fall down. We understand it a little bit better than that now. Even before Columbus sailed, people knew the Earth was round. The only dispute was over how big it was. And so people knew that gravity was the tendency of things to fall towards the center of the Earth. It was Newton who, I've actually looked into this story. It may actually have happened that he watched an apple fall, and this was gravity, and he looked up at the moon, and he realized, oh, it's gravity that's keeping the moon going around the Earth. That must have been one of the most exciting moments in his life, to suddenly realize that maybe it's gravity that keeps the moon going around. You would think that the moon, which is going around the Earth, it has this velocity, so why doesn't it just shoot out that way? Why doesn't it keep on going in a straight line? After all, once in motion, things tend to stay in motion, and the pull of gravity keeps it down. Now, let me illustrate this. We're really getting into how satellites work, the fundamentals of satellites. So, a little hose here. I'm going to shoot some water. See if I can get this to work. There we go. Because I'm shooting water horizontally, and it begins to fall. Because things tend to fall. Now, if I tilt this back, the water will go further. It may go off the edge if I don't turn it down a little bit. Let me turn that down a little bit. Okay. And look at that path. It's sort of a hoop, a hill-shaped thing. The path is actually, if you ignore the air resistance, it's the shape of something called a parabola. And the water's moving this way, and if there were no gravity, it would keep on moving. But because this gravity gets pulled down, and it goes in this curved path. So gravity does that. Now imagine just for a moment that instead of this being 120 centimeters, it was 12,000 miles. And so the stream goes up like this, and it's being pulled down 12,000 miles away. The only problem is it wouldn't hit the Earth. Would miss. Let's see. So here we are on the Earth. Here we are shooting our water off, and it starts to fall. Well, now it's going horizontal again, so it keeps on falling. But the Earth is bending away from it. So even though it's constantly falling, it never hits the Earth. And this is what Newton realized. The pull of gravity will hold it in. But if it's going at the speed where it will never hit, and then it'll actually go around forever, like this. In some ways, this was one of the first unifications of the laws of physics. You may read about that in the newspaper. People are always trying to unify the forces of physics. Well, this is back 1600s, I guess, and Newton unified the laws of physics. What he recognized was these two separate laws, the law of gravity and the law of the moon going around, celestial motion, was actually just a manifestation of gravity. And I like to think back in history and try to imagine what it was like before you understood that. Now we take it for granted because you learn it, when you're 2 years old. This is interesting. I don't know how many people here throw the discus or a shot put or something like that. But one of the interesting questions that's kind of fun is, what angle should you do it for maximum range? Okay, some people said 45. What other answers do I get? 30. Is that a guess or an answer? It's a guess. Anybody know? Yeah. Should be 45. Anybody else know? Last semester when I taught this course, there was a shot putter in the class. I'm trying to remember the numbers. I think I put them in the text. It was less than 45 for the shot put. Discus, I think it got down to around 41. The reason was because of air resistance. So in real athletics, when there's really air out there, I mean, if you do it where there's no air, I guess you do it differently. But watch what happens. Here it's horizontal, so it starts falling and it hits. If you let the white line be the ground, it hits the ground right away. If I tilt it back, it spends more time in the air because it's going upwards now before it hits the ground. And some of its velocity is horizontal, so it goes further. If I tilt it even more, now what's happening is it spends more time before it hits the ground because it has a larger component of upward. Because some of the velocity is going upwards, if I could move this thing, if I could run with it, or let's put it another way. Let's say we all ran with it. Let's leave this here and all run this way, and I'll watch this water. What I would see was that here's the water, and it's going up, and it's coming down. That would be a relativity experiment. If I were to do that, we'll do a demo of this in a moment. But here's something I'd like you to think about. It's not at all obvious, but if I were to do that, suppose I had this water with the same upward component of velocity. If this is moving upwards at 10 centimeters per second, I don't know how fast upward the velocity is. If it had the same upward velocity, it would get to the same height and would reach the level at the same time. Let me do that another way. I'll demonstrate with this chalk. Here I am. I'll lift it up. It takes a certain time for it to come down. If I throw it about this high, it takes a certain time to come down. Now watch this. I'll do the same thing. The claim is, if you measure this accurately, you'd see it at the same time. To me, it's obvious because to me, you're moving, not me. Your whole classroom is moving to the side, and I'm throwing this thing up, and it comes up, and then it comes down, and I catch it. And if I stand here, it throws it up, it comes down, I catch it. The fact that it's moving sideways doesn't affect its vertical motion. This is a fascinating insight in physics. So here, it takes longer to come back down because it has some of its velocity is directed in the upward direction. Now, I can put all the velocity in the upward direction, and it takes a long time to come back down. But it doesn't go very far in that time because so little of the velocity is in the forward direction. So in the absence of air, some of the students already knew the optimum angle is 45 degrees. But in the presence of air, it's not. You all know if you want to throw a frisbee for maximum range, you don't throw it up at 45 degrees. A shot put is closer than most things to that ideal. But even the discus. Here's an odd thing I learned about the discus. Well known to... do we have any discus throwers in the group here? I don't think we do. But the oddest thing about the discus is the records were set in a competition in which the wind was blowing. Now, most sports make it, you can't set a world record when the wind is blowing, but with the discus you can. So the discus players who set this, they all know the secret to take maximum advantage of the wind. Usually when you're throwing the discus, there's a certain angle over which you can throw it. If the wind is coming from that direction, you throw it right into the wind. That really surprised me when I learned it last semester. But the reason it works is if you throw it into the wind, you can move the discus in such a way that it stays up longer. But the wind coming to it holds it up in the air longer, it winds up going further. So these things are tricky and complicated, and most physics professors don't know that you should throw a discus into the wind, and I didn't even know that until last semester. Things are much easier when there's no atmosphere. The air makes things complicated. Newton worked out the case when there was no air. Air introduces friction. Friction is hard to understand. A lot of physics will talk about those realms in which we don't have air, we don't have resistance. Question? You're saying it's the question, he says that for artillery, the maximum is actually 45 degrees. That surprises me. I would expect it to be a little bit less. So the question is, why is this, he wants me to explain why this answer that strikes me as being wrong is correct. And I find it hard to answer that. You're telling me, figure out why you're wrong and then give the explanation. I find that hard to believe. My guess is it would be a little bit less than 45 degrees. If you have a very massive thing, the air resistance is not very much, and maybe the 45 degrees is a rule of thumb. But typically, one uses tables in order to estimate these distances in the military, or these days, a computer. And 45 degrees is probably what I would guess that was an old rule of thumb, because it's close, because these things are so massive that the air resistance doesn't play that much of a role, at least for short distances. But I'm willing to bet that it's not 45 degrees, a little bit less. We could try to resolve that. So the satellite opts in this way. Now think about this, what it means. So this water here is being shot out, or hello? Take this chalk here. Now watch it once again. Now I throw it up and it's falling. Okay? Now I throw it up and it's falling. It was falling even though it was moving in an arc. This water is falling even when it's moving in an arc. This satellite is falling even when it's moving in an arc. Think of a satellite as something which is in perpetual state of falling. Now, what happens when you fall? What does it feel like when you fall? You've all fallen. If you fall a short distance, most of what you feel is the ground. If you fall a larger distance, and typically I did this when I was a kid. I jumped off something high just to see what it was like. It was very scary. We have an instinct to not fall. We know that the ground comes up really fast. How fast does it come up? I put down a number here. For every second that you fall, let's see, did I put it up here? You gain 22 miles per hour. For every second that you fall, this is called the acceleration of gravity. It's given the symbol G. G is 22 miles per hour every second. So if you're falling for 2 seconds, you're going 44 miles an hour. Now, 22 miles per hour, how fast is that? That's about as fast as a fast runner can run. You can run a little bit faster than that, the real sprinters. But if you go fast, you're probably about 22 miles an hour. So you fall for 1 second, imagine yourself running as fast as you could possibly run into a brick wall. That gives you an idea of what it's like. 22 miles per hour doesn't sound like much, but into a brick wall, it hurts. After 2 seconds, you're going 44 miles per hour. 3 seconds, 66. So you see you're gaining speed every second. That's called acceleration. A little bit of an aside here now. Let me give an illustration. some of you may wish not to listen to this because it may just confuse you. So be prepared to forget everything I say in the next 2 minutes or so. Physicists take this and they prefer the units. G is equal to 10 meters per second every second. Because 22 miles per hour is about 10 meters per second. So that's the number they use. They actually use 9.8 just so that you have more fun with your calculator. 9.8 is more accurate. Now, they usually refer to this as 10 meters per second squared. Just because that's fun with math. You have a per second, call that per second squared. Then you start thinking about square seconds. And this is where a lot of students just leave physics. Okay, but really all it is the speed you gain per second. And there's no such thing as a square second. That's just the way the math looks when you do it that way. So this is the number, 10 meters per second every second. That's the number that I'll use when I do some calculations. That's the acceleration of gravity here at the surface of the Earth. If you are in space and you are falling towards the Earth, you better make sure that you go fast enough horizontally so that by the time you fall down, the Earth is also curved away. And that takes about 8 kilometers per second. So this is called the orbital velocity. This is what's orbital velocity for a low Earth orbit, or a LEO. I'll explain what I mean by this in a moment. Be advised that I found a mistake in the textbook. There was a place where I discovered when looking at it last night that I had dropped a factor of 10. And so this morning I posted a new version of the textbook with the calculation for low Earth orbits fixed. It was just one minor calculation having to do with how fast a satellite passes overhead. And I caught that error, so I posted that new one. So if you're going 8, now imagine what it's like to be falling, but you're in orbit, so you keep on falling. So the way this works, suppose there's an amusement ride that I went on a few years ago. They've changed the name since then, but it was at Marriott's Great America. I don't know what they call it now, but now it was called then the Edge. I'll never forget the Edge. Edge was a wonderful thing. All amusement park rides are designed to do one of two things. They're either designed to make you sick or to really scare the living daylights out of you. Both, maybe. Anyway, the ones that are designed to make you sick, I stay away from. But I kind of enjoy being scared now and then. So the Edge was supposed to be scary, so I tried that. And it's a tower. And it has some tracks on it. Like this. And a little elevator. You get inside here. And it's an open elevator, so you're looking right out. And it take you up. I think it's probably over 100 feet high. Anyway, and then what happens is they have this little mechanism, and the elevator moves out over here. And it has some things loosely holding onto this track. But basically, you're suspended there in space, and then without warning, they release you. Okay? And so you're free fall. And it's only a second and a half or something like that. But it's more free fall. The most free fall I'd ever felt before was once I jumped feet first off a high diving board. I said once. When I went on the Edge, I was prepared to do a physics experiment. I wanted to sense the weightlessness for over a second. So I had with me something like this, and I was going to, as soon as I fell, I was going to let go of it, and I would see it float in there, weightlessness. And then what happens is because of these rails, you only free fall about this far. And then the rails gradually come like this, and you wind up stopping feet first down at the bottom. So I will now try to give you an idea of what this experiment was like. Okay, so here I was on the top, looking out over the countryside, looking kind of high. Okay, here we go. That's an accurate depiction of what happened. The experiment was not successfully carried to fruition. And I discovered that I have an extremely deep instinct to grab something when I feel like I'm falling. And it's probably a very deep survival instinct that we've had over the years. If you're falling, grab for something. But I wondered about the astronauts, because you see, if you're in space, you're constantly falling. And so if I were in space, I'd take this thing and I'd let go, and it would just float there in space. Now, in fact, we're falling. You see, when you're in orbit around the Earth, you're still feeling the force of gravity. You are falling, just like I was feeling the force of gravity when I was falling down the edge. It was the gravity that was accelerating me. But I feel weightless. What does that mean? It means there's no force on my feet. See, right now, the only reason I'm not going through the floor is the force on my feet is keeping me from going down there. But when you're jumping, there's no force on your feet. This is a weird thought. My tongue is on the bottom of my mouth. I don't know if that's because it weighs something. If I were weightless, it wouldn't be. My internal organs would all be sort of floating inside of my body. This is what gives you that strange feeling when you jump off something, of the feeling of weightlessness. You're all falling. When everything in you is falling together, that means you feel weightless. And the astronaut is not outside of the Earth's gravity. The astronaut is simply constantly falling. So having been through a second and a half of falling, I found myself in a conversation with Sally Ride, the astronaut. I had to ask her about this. How can you stand this I wanted to ask her how you be up there for weeks. So I said, Sally, let me tell you about this thing called the edge that I was on. And so you go up like this, and there's some tracks, and they move you forward like this, and then they release you. And she went, ooh, that's scary. So wait a minute, Sally, no. no. Look, hey, you were weightless. You were weightless for a week. How can you say this is scary? And she said, oh, you get over it after the first second or two. So it's only the first second or two that's really scary. So this is gravity, and this speed is the speed you need so that the pull of gravity, which accelerates you downward. So when you put a force on an object, it starts moving. Typically, if you put a force on an object, it will move, and if you keep putting the force on it, it keeps on moving faster and faster. It gains a certain acceleration. For the force of gravity, the acceleration gain is 22 miles per hour every second. If you put a bigger force on it, it will accelerate more. If you want to know how fast it's going, you say, how long was that force on it? And how big was it? Well, actually, this is the equation. If you have a force, and you'd like to know the acceleration, what you do is divide by the mass, and that gives you the acceleration. Depending on the units, typically these units are designed to give it to you in meters per second. But if you remember that 1 meter per second is 2.2 miles per hour, you can translate it. I mean, in Europe, what's the velocity of a meter per second? Well, I'm going, a meter every second. That's a meter per second. It's a nice number. 22 miles per hour. 2.2 miles per hour is also going 2.2 miles per hour. And a really fast walk, when I'm really in a hurry, I average 3 miles an hour. When I'm taking a nice vigorous walk, I go 2 miles an hour. Backpacking, I typically average 1 mile an hour, with 60 pounds on my back. But if you put a force on an object, that object will get going faster and faster as long as that force is on there. Just like something falling in gravity gets going faster and faster as long as, well, it doesn't happen for the astronaut because the astronaut is always changing its direction. And although the force of gravity is actually turning the direction of the astronaut as opposed to speeding it up. It'll wind up going the same speed as it goes around. So force can also change direction of the object as well as making it go at a faster speed. So this is the basic equation, and it says if you put a force of gravity on me, well, what's the force of gravity on me? It's the pull of the Earth on my body. That's what we call the force of gravity. This is, Newton figured out that the force of gravity is actually a force of attraction between mass. So, for example, if you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. You're pulling it up. Now, you may, you say, hey, you don't have much mass, so you can't pull very much. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things, more effectively than even neutrinos. You're pulling on atoms right now on the other side of the Earth. They're far away, so it's not as strong. In fact, your force of pull depends on the distance. The rule is given here. The force of pull goes as 1 over r squared. So we say the force of pull for gravity. It's a bunch of constants. Well, it's g times the mass of the first object, mass of the second, divided by r squared. I'm not even going to ask you to know this. What I do want you to know, but you may want to play with this, because it says if something is twice as far away, there's gravity between my two hands right now. The masses of one hand, first hand, and the second hand are kind of small when you plug in the constant here, and so the force isn't very big. G is 6 times 10 to the minus 7, if I remember correctly. So the force of gravity isn't very much. But if you have enough fists, and have a whole Earth made of fists, then it all adds up. So we're being pulled in every which direction by gravity. But because the Earth is a sphere, it all feels as if, the sideways forces tend to cancel. That thing over there and that thing over there are pulling me in opposite directions, but they cancel each other. So the net effect is this, as if I'm being pulled straight down. Oops. Let me show you that again. Here's the Earth. Here am I. Every bit of mass is pulling me in its own direction. These forces are weaker than these because this is closer. And the close forces have more force. It's the 1 over r squared. You go twice as far away, the force is 1/4. Go 100 times as far away, the force is 1/100th squared, which is 1/10,000. So most of the force is coming from nearby stuff. And that's pulling me straight down. Now suppose the Earth is not a completely uniform sphere like this. Suppose there's a hole over here. What do we fill that hole with? Well, you could fill it with vacuum, but those don't really exist. Let's fill it with something that's much lighter than rock. You could fill it with rock, but then it wouldn't be a hole. Fill it with something that's light, like oil. So let's make this oil. Now look at the gravity on me. The rock over here is pulling me down this way. The oil over here is pulling me, but not as much. They no longer cancel. So if I have a very accurate meter, I can search for oil by looking at the gravity anomaly. The fact that the gravity is no longer straight up and down, but that the rock over there is pulling me more than the oil over there. So this is one of the most effective methods being used today in searching for new oil deposits, is using gravitational mapping. So they make maps. Here's a map. This is a map that was it's a gravity map. Now, okay, you measure the strength of the gravity. You can measure the direction of the gravity. That's harder to do than just measuring the strength. So typically what they'll do is they'll fly an airplane and measure the strength of gravity. And then if there's some oil around, it'll be less, because this nearby rock is missing. Now what they do is they fly back and forth over the land, making a map of the gravity. And then they're looking for strange things that might be under the ground, things that have more gravity or less gravity. More gravity might be a lead deposit or uranium. Less gravity, which is where it's mostly used, is for the oil industry. Now, once you've done that, you've measured the gravitational strength everywhere, you can assign it a color. And say, blue is low gravity, green is high gravity, and you make what looks like a map. And it's a gravity map. It's a representation of the strength of the gravity. And if you say high gravity, you can even contour it so it looks like a hillside. Here's a gravity map. This is in the textbook. There's a gravity map, and there's something very interesting in that gravity map. Look at that mound right in the center. It looks like rings. How big is this thing? You'd be amazed, but there's actually a scientific debate over how big this thing is, as if it matters. Why is there a scientific debate? Some people say this is the biggest ring. Other people say, no, see that out there? Oh, there's evidence of a bigger ring. Why? Well, it turns out this is in Mexico, and this photograph was taken over the Yucatan Peninsula. And you can't see the peninsula here because it's measuring gravity, not ocean. And the ocean is pretty shallow there anyway. But here's ocean on this side, and this is Yucatan on this side. And this is a structure that we now know was created 65 million years ago. This is the location of the impactor of the comet or asteroid that wound up killing the dinosaurs and extinguishing most life on Earth. And the way this ancient crater was located. You see, 65 million years ago, you get a crater. It doesn't stay a crater. It gets filled in with water. And the sediment begins to fill up. And pretty soon, you don't see much of a crater there. But this gravity map allows them to find the crater because the sediment that filled it up had a different amount of mass, different density, than the material, than the material that was there previously. So this is how the crater that killed the dinosaurs was found. Let's get this. By gravity mapping. Gravity mapping, I've seen it used very effectively to find tunnels that go from Mexico into the U.S. for smuggling drugs. They have gravity maps. Now, they put them in a car. The ones they have now actually don't work so well. What they have to do is, if they have a suspected tunnel somewhere along here, they put the car here and they wait there for 15 minutes measuring the gravity. Then they move it a little bit further and measure the gravity. Very slow, but they're improving the technology very quickly because this has already found at least one tunnel. It was a 300-foot long tunnel that went all the way from the Mexican border, from a little shack that was 50 feet on the other side of the border to a tiny little shack that was several hundred feet on the other side. It was being used at night, and they found this by looking at the gravity. So when you're over a tunnel, there's a little bit less gravity because of the Earth not being there. Now, an odd thing about this, usually we assume the gravity, the Earth is pretty, well, it is pretty spherical. It takes very precise measurements to see any difference in that. And so the net effect is that the gravity is coming from straight down. And one can show by using the mathematics that you get exactly the same gravity if you put the entire mass of the Earth at one point, and up here just had a hollow shell that you stood on. And you'd feel exactly the same gravity as you do with the filled up Earth, as long as the total mass was the same. This is a point that confuses a lot of people. So I mention it partly because it helps you understand black holes in a key way that many people misunderstand. Let me say this again. If you're standing on a spherical surface like this, you feel the force of gravity. You'd like to know how big that force is going to be. It's hard because you've got to add up all these things. That's a three-dimensional integral. And you can do it. I've even done it. But there's this rule of thumb that works and perfectly correct. If this is a pure sphere, then it's exactly the same force you would get if all the mass were at the center. Now, the reason this relates to black holes is the following. Suppose here's the sun. We haven't really told you what a black hole is. We'll be getting to that soon, too. Here's the sun, and here's the Earth going in orbit around the sun. Constantly falling, by the way. We go around the sun. We're like falling towards the sun, except we always miss it. We wind up going, it's not quite a circular orbit. The orbit is slightly egg-shaped. We call it elliptical. But only by a couple percent. I think a little over 1%. The force of gravity is the same that we would get if that sun were simply a point mass located at the center. The fact that the sun is spread out doesn't really change the gravity. It does a little bit because the sun isn't completely uniform. But approximately, very closely, approximately, it's the same as we'd get from there. Now, suppose the sun were to suddenly collapse into this thing called a black hole, which I haven't described yet. Just one startling conclusion. A black hole is something which has the same mass, but in a very tiny volume. A black hole, if you took the sun and stuffed all of its mass into something the size of the Earth, then you would have a black hole. And you could ask, what would that do out here if there was a black hole in here? The answer turns out to be nothing. Well, we wouldn't have the sunlight, but other than that, the gravity would be the same. See, we're the same distance from the center. And a black hole having the same mass as the sun would be the same gravity. Science fiction sometimes gets this wrong. They think a black hole sucks everything in. Well, it does if you get really close. If you land on the black hole, you have all this huge mass. Let's go in here. Let's say this thing turned into a black hole. And we have this huge amount of mass that's all stuffed into the size of Berkeley. So here we have something the mass of the sun. And the distance to the center, if we get to the surface, is just 5 miles instead of it being 93 million miles. And so if we use our gravity equation, which you don't have to know, this gravity equation, we have the same mass as we had before, but now we've made r much smaller. You divide by a small number and you get a huge force. So the key thing about a black hole is that you can get super, super duper fast. I guess I just bore some people. Okay, now what is a black hole? Well, I mentioned this thing here about going to orbit around the Earth. How high do you have to go to orbit? I want to talk now about different kinds of satellites, about escape, and about black holes. So the first question is, how high do you have to go to orbit? And this is an important fact that many people don't appreciate. The answer really has very little to do with gravity. It has to do with the Earth's atmosphere. If you try to orbit, suppose you're on the moon. Let's see, let me find a nice board here. You may have seen things like this on the moon. Here's the moon. Suppose you want to go into orbit above the moon. How high do you have to go? 100 miles? 1,000 miles? Well, actually, 1 inch would be enough. Except you might run into a mountain. The main problem with orbiting the moon is avoiding the mountains. You don't have to get up high, because all you have to do is to make sure that as you fall, you keep on missing. But on the Earth, we have this atmosphere at the bottom. With all this atmosphere on the Earth, if you go 8 kilometers per second, pretty soon you'll slow down just by all the air resistance. So on the Earth, the only reason you have to go up high to orbit is to get above the realm of the air resistance. That's the only reason. How high do you have to go? Well, it depends on how long you want to stay up. Some people say 100 kilometers. Well, the fact is, if you're orbiting at 100 kilometers, you'll probably come down after 1 or 2 cycles because you lose speed against the air. Once you lose speed, you fall the same amount, but you don't move forward as much. I have a demo I'd like to show on this. We have our volunteer monkey up there. And he has agreed to let go of the tree and fall to the ground. In exchange for that, we're giving him a little bit of food. So I have a gun here designed to shoot food for the monkey to catch. And I'm aiming this right at him. So there's my laser sight, aimed right to his arms. By the way, people who took this course previously may have told you about a demo that we used to do called Shoot the Monkey, but we don't do that anymore. Now we feed the monkey. Okay. Now, if we were in space, the light beam is going in, actually, not quite a straight line. Why isn't the light beam going in a straight line? It turns out it's bent a little bit by gravity. But it's not enough to be measured here because it's going so super fast, going so much faster than bullets go. So because of that, it's about a straight line. And if we were in space, I would just shoot this at him, and he would catch it and have his little bit of food. But because there's gravity here, the thing will start falling. Now, think of falling as being with respect to where it would be if it were in space. It's instead of being in that straight line, it's now falling from the straight line. It's just like the water here. It was going that way, but it starts to fall. This thing will fall too. How much will it fall? Well, it depends on how much time. It gains 22 miles per hour of downward velocity every second. Suppose it takes a second to go there. Oh, by that point, it's moving downwards at 22 miles per hour, and it's somewhat below the path. What about this monkey? Well, if I can get him to let go at the same instant that I fire, then he will also be going down at 22 miles per hour every second. And if it takes a second to get there, they'll be at the same spot. So as long as he releases at exactly the same instant I have here, he should be able to catch the food. Okay. To help him do this, we put a little wire right across the gun here. I mean, the food deliverer. And when the banana comes out, it breaks the connection of the wire. That then turns off a magnet, which is right up there. So he doesn't even have to think about it. He'll just start falling. Sort of like me on the edge. And if he has his act together, he can then catch the food. So let's see if I can do this. Let's see, I lost my reading glasses. Let me make sure I was set okay. Okay. So let's turn up. We're going to actually shoot the banana with air pressure. So turn up the air pressure here. And we'll suddenly release the air pressure. That will put a force on the the banana or the food, and that will accelerate it outward. It will accelerate as long as there's a force on it. The force is gradually decreasing because the gas is expanding, so the pressure isn't quite so much. So it gets most of its acceleration here. But the acceleration depends on the force. That's F equals ma, which is Newton's fundamental law of physics. Now, let me turn this down a little bit. I'll release this a little. I don't want it to come out too fast. Okay. About where I want it. So now what we're going to see, if this were in space, it would be in a straight line, it would go right to them. They're both falling, but the claim is even though this is going horizontally, it's falling at the same rate with respect to its path that guy is. 22 miles per hour every second. So let's see if I can get this to work. You ready? Watch the monkey, watch the gun, watch the combination, see what you can see. Well, it worked fine except he forgot to catch it. We did hit the monkey. Okay. Where'd that ball go? Did anybody find that? Oh, there it is. What is it? I don't blame him. This is not very edible. No wonder he didn't catch it. Okay. So let's get back into space now. We're talking about orbiting. Suppose, so you could orbit just above the surface of the Earth if there weren't the atmosphere. So you have to get above the atmosphere. How thick is the atmosphere? Not very much. You go up about 5 miles, and you have half the atmosphere. Go up Mount Everest, and you have, I think, 40% of the air that you have down here. So you have to go higher than Mount Everest, but it falls off it very rapidly in a way that follows a half-life rule. If you get up to 100 kilometers, it's not really enough, but if you get to 200 kilometers, it's pretty good. So to go into orbit, the first thing is get above the atmosphere. The second thing is get enough speed that you can get all the way around. How much energy does it take to do both of these? Almost all of the energy is to get above the atmosphere. That's the hard, is to get the speed. Getting above the atmosphere isn't that hard. It was done many years ago with the V2 rockets. And so getting up is not the hard part. But getting that speed, I actually work out the numbers in the book. And, see, do I say it here? Up there. Yeah, it takes 30 times as much energy to get the speed up as it does just to get up 100 kilometers. You have to do both. So if you're going to get to the speed, getting up 100 kilometers isn't that hard. Typically, you'll watch the rockets take off vertically, get altitude, and they quickly start turning because what they really need is the speed. And it takes 30 times the energy. That's more than 5 times. Just going straight up to 100 kilometers isn't much. Amateurs can do it. There was an amateur competition with rockets. It was done by Goddard in the 1940s. But going horizontally to that speed, you have to have 30 times the energy. That typically means 30 times the fuel. That wouldn't be so bad. 30 times the fuel. It's only 30 times bigger. Well, no, it's not 30 times bigger. The reason is you got to get that the fuel. It isn't exploded all at once like in a gun, but it's exploded slowly. So you have to have enough fuel to carry the fuel up, so that you can release the fuel gradually, so that the acceleration is low enough that you don't crush the astronaut. So getting someone into orbit is enormously harder than getting them up to 100 kilometers. You wouldn't guess that if you'd been following with any excitement the X Prize competition. The X Prize competition is something that was in the newspaper about a year ago. They wanted to have a private company get humans into space. So how do you get them into space? The trick was you had to be able to fly them up to an altitude of 100 kilometers in a rocket. And so the X Prize was finally won last year or about a year ago, by a company that managed to get people into space. And if you think about it, they did the easy part, getting up 100 kilometers. So the things that we did with a U-2, not a U-2, with a V2 rocket back in the 50s. But they were nowhere near getting into orbit because that requires that horizontal velocity. Nonetheless, the X Prize got a lot of newspaper coverage, I think by people who didn't know the difference. But don't the people who won the X Prize know the difference? Yeah, they know the difference. Therefore, they're not intending to ever put anybody into orbit. Their vehicle is completely useless for putting people into orbit. It would have to deliver 30 times the energy. So what are they going to do? Very interesting. Think of Jurassic Park. What do you do when you have a scientific breakthrough? You make an amusement park. So what they intend to do with this rocket is to send people up 100 kilometers. When they come back down, they can certify that they are now astronauts. So you get wealthy people who will go on this ride so they can say, I'm an astronaut. And that's how they'll make a business model out of this. But they're not going to get things into orbit this way. If you want to go into a higher orbit, and you frequently do, why? Well, let's take a look at this low Earth orbit. And let's look at some of the numbers. In the low Earth orbit, you're really close. That's really useful if you want to be a spy. You want a spy satellite, you want to have a camera, you want to look at the Kremlin or Beijing or wherever, North Korea. You want to look at North Korea and see what sort of nuclear things are they building these days from a satellite. So what do? Well, you don't want to be way out here, thousands of miles away, any more than if you're taking a picture of your boyfriend or girlfriend, you want to stand back 100 feet. You're getting real close. So the cameras have to be in close. They make them as low as they can, typically 200 kilometers. So here we have something whizzing overhead at a height of 200 kilometers, and let's look at that number. This is very important for future presidents. Very fundamental result. So here we are, and here's the Earth. And here's the satellite going over at an altitude of 200 kilometers. And it's looking at this little nuclear plant here to see whether it's getting electricity. You can tell some things. A big power plant, you can look at the electrical lines going in. You could try to measure how much heat is coming from this using invisible light, something that we have a whole chapter devoted to later on in the semester. So you want to study this as best you can using whatever remote sensing techniques you can. Now here's the problem. You're moving 8 kilometers per second. So you don't stay over it very long. How long do you stay over it? Well, let's just draw some triangles here. Here you're approaching it, and this is 200 high, this is 200 that way. This is also 200. So you're over it for basically 400 kilometers. You're over it there too. You can still see it, but you're so far away you can't take good pictures. So the useful amount, you're over for only 400 kilometers. You're going 8 kilometers per second. So you cover those 400 kilometers in 50 seconds. About a minute. So the spy satellite is over the location for about a minute. I want you to know that. A lot of people think spy satellites can hover. No, we use airplanes for that. Or drones. We use non-human airplanes now. You may have seen in the news a few weeks ago that we took some shots at the second Al-Qaeda figure, Zawahiri, and apparently missed because he came on television making fun of President Bush yesterday. Ha ha ha, try again. That was done from a low-flying airplane. It was without any human in it. It has TV cameras. It can hover, it can watch, and it can shoot. It's called the Predator. So the Predator is an airplane. But the satellite doesn't hang around for more than a minute. So what happens in North Korea? Well, let's take a look at the Earth now. You have to get within 200 kilometers here to see it. Likewise, you better not be more than 200 kilometers off to the side. So if we have a big picture of the Earth here, and here's Korea, Japan, and so on, and the satellite is flying over, very close to the surface because you want it to be a low Earth orbit, just hugging the surface. It's over it for 1 minute. You get all the pictures you can. Now the satellite goes in a circle and it comes back. But by that point, the Earth is turned. At 8 kilometers per second, how long does it take to go around the Earth? Another number you should know. It's about an hour and a half to go around the Earth. You can work that out. I mean, it's 24,000 miles around, and so it turns out to be about an hour and a half. So when it comes back, unfortunately, North Korea isn't there anymore because the Earth rotates. It's an hour and a half. It's probably, it's 24,000 miles around at the equator in an hour and a half. Up here, where North Korea is rotating around, it's probably more like, 15,000, 20,000 miles. Let's say 24,000 miles. It's going 1,000 miles an hour. It's a couple thousand miles. It's 1,000 miles away, 1,500 miles away. It's so far away you won't see it on the second orbit. This keeps them going around. The Earth, meanwhile, rotates. Bummer. How do you spy with these things? Well, it's not easy. You put more of them up there. How many do you think we have up there? How many spy satellites do we have up there? The number's classified, but people on the web try to keep track of this. And they claim the number is just a few, like 3. So, not easy to watch the world from a satellite. What about Google Earth? We have the entire Earth. Satellites. Well, there are a couple things in Google Earth. One is the pictures, they're kind of out of date. You look at them and you see, oh, 2 years ago. By the way, if anybody here hasn't used Google Earth, it's one of the most fun things you can do. I mean, you put in your address, and it starts off wherever it is. I don't know, maybe we went to Mount Everest. And then you put in your address in Berkeley, and then we show it sometime. Then you go zooming out, and then you go flying over, and then you land right in Berkeley and zoom right into a close-up of your house. Really a wonderful free program. But those photos are old, and they were taken at high altitude. And if you try to see any of the details of your house, you'll be disappointed. You could probably identify your house, but you won't be able to identify any automobiles, certainly not read license plate numbers. Now, we'll be talking about how good you can do when you get up close. It depends on the physics of light. And I'll show you that you probably will never read license plates from space, but you get close. But if you really want to track Osama bin Laden, you need something which is lower and closer to do that. So there's a lot of people simply assume the U.S. has satellite coverage of the whole globe. And the numbers are so far from that. But you need to know that. So this issue of how do you dwell? Well, one answer is you go into a high orbit. Now this one is actually called a medium Earth orbit. MEO. It may be 12,000 miles up. And maybe you orbit then a couple times a day instead of every hour and a half. In that case, you'll be up here for quite a while. You could also go to a high orbit, HEO. Suppose you go to a high enough orbit that you go around the Earth once a day. And let's choose it over the equator. So here's our high Earth orbit that's right above the equator. Now, if we do it just right, the Earth is turning this way, we're up there, you'll stay above the same place. It's about 22,000 miles up. It's only 1/10 of the way to the moon. It's 5 Earth radii up there. But now you're in an orbit that has its own name called GEO. Geosynchronous. With geosynchronous, it has to be above the equator to really be truly geosynchronous. Why is that? Well, if you're above the equator, watch this. Here's the orbit above the equator. Looks like Saturn, right? So here's above the equator, and the Earth is turning, and you're moving. You're higher, so you're moving faster than the surface of the Earth, but you stay above the same point all the time. Okay, suppose you're up here. Suppose you have your orbit like this. You go around once per day. Well, right now you're right above that spot, but this thing moves over here. And you're moving down here. Pretty soon you're in the southern hemisphere. So the only way you can be truly geosynchronous is by staying above the equator. This becomes a very important international issue. The reason is it gets kind of crowded. We are filling this place up with geosynchronous satellites. What do we do with geosynchronous satellites? Well, weather satellites, for example. If you look on the web and you find a weather satellite for Berkeley, you'll see a photograph that's updated every few minutes. But they have a satellite that's dedicated to the West Coast. You have another satellite that's dedicated to the East Coast. So these are taking pictures. They're very far away, but you don't have to be able to see individual clouds or raindrops. All you have to be able to do is see where the storms are. They have them in different colors. Some of them, what I call invisible light, in the infrared, because these can sense the amount of moisture and other features of the. But these are in geosynchronous, so that you can always get a picture. Some of them will even operate at night. They have visible and they have infrared. The ones that operate in the visible, you see, night is very boring. It's just a lot of black. But the infrared, you can still see signals at night, and you can see the cloud cover from that. It has to be, and it's getting crowded. What else do we put up there? Well, I have the luxury of a satellite TV dish. The instructions are, get up on the roof, take your dish, and try to point it at the right satellite. Now, the satellite has to be above the equator. Why is this? The reason is, once I've pointed that satellite, I don't want to touch it anymore. I want the satellite to always be right there. That will be the case if it is above the equator, and if it's in a geosynchronous orbit, so it goes around once every day. Then it will stay in the same location of the sky with respect to me. Of course, it's moving around the sun, it's moving around the Earth, but it's going around the Earth at the same rate that the Earth is turning. So my satellite coverage like that. Now, why not put a geosynchronous satellite to observe North Korea? The answer is it's just so far away, it wouldn't get much better resolution than you can from a weather satellite. Build a better camera. Well, in principle, you could do that, but the camera would have to be the size of a football field. And we'll talk about that when we get to optics, about how big the camera has to be in order to be able to see things. So that's the most serious limitation right now for spy satellites. Weather satellites. What about medium Earth orbit? What do we do with a medium Earth orbit? One of the most interesting things we do is GPS, the Global Positioning System, GPS. How many of you own a GPS receiver? How many of you have ever used one? I have one in my automobile. You know, I turn it on, and it picks up the signal from the satellites. Works in a very interesting way. I want you to understand how a GPS receiver works. They're in medium Earth orbit. What that means, it'd be really interesting to think about why that was the case. But let's understand how it works. Then you can see why they picked a medium Earth orbit. If here's the Earth, and you are right here, and you'd like to know, you don't know where you are, one thing you can do is to contact radio stations. And there's an old system called LORAN that worked this way. And by timing, you can get your distance to radio stations. LORAN actually uses the differences of distances between two radio stations, but that's a detail. If you know you're a certain distance from a radio station, then let's look at the map here. Here's California. And here's Nevada. By the way, the biggest surprise, I think, of the satellite maps that anybody ever showed me is the fact that these images from satellites actually show the state boundaries with these solid lines on them. I never realized they were visible from space. Laugh louder, please. Now, suppose you're here lost in the desert somewhere. You could locate yourself if you knew how far you were from San Francisco. Well, not really. You'd only know if you knew the distance from San Francisco. You'd know you're on the circle somewhere. But suppose you also knew your distance to Los Angeles. If you knew that distance, you know you're on that circle somewhere, and where they cross, that's where you are. This is the same principle now for the GPS satellites, except the satellites are moving. Well, no problem these days. You got computers. So your little GPS receiver is not just a receiver, it's also a computer. It picks up a signal from the satellite. The satellite tells it when it emitted that signal and where it was when it emitted it. It's like saying, you know, it's like you may pick up a signal from here, from San Francisco, and it says, by the way, I'm the San Francisco signal. And this one says, I'm the Los Angeles signal. So the satellite says, and my location is blankety blank. It also tells you when it emitted that signal. Now, how do you know how far away it was? You look at the time that you receive it. And from the speed of light, you can tell how far away you are. What is the speed of light? It's sort of a nice number. It's in 1/billionth of a second, it goes 1 foot. That's how fast light travels. What is 1/billionth of a second? It's about 1 computer cycle. If you have a 1 gigahertz computer, that's 1 cycle on the computer. Light goes that far. Not a surprise that computers are small, right? Because in 1 computer cycle, no signal can go more than a foot. So computers have to be small because light is, that's fast. 1 computer cycle, 1/billionth of a second goes a foot. But it's also slow. It's slow enough that if the satellite tells you when it emitted that signal, and you know when you received it because you have a clock too, then you can tell how far you were from the satellite. Now, if here's the Earth, and there's a satellite here, you know you're a certain distance from it. What that actually means is that you're on some sort of a circle on the Earth. You're on that circle somewhere. All the points on this circle are the same distance from the satellite. You know your distance, so you know you're on the Earth. So your little GPS receiver has to have a map inside of it. if you had two of these, let's say there's another satellite here, then you know you're right on the intersection point. Typically, you require 3 satellites. It's better to have 4 because then you don't need an accurate clock. But this is what's happening. Now, where do you put the GPS satellites? Do you put them in low Earth orbit? Let's say 24 GPS satellites are in low Earth orbit. You get to see each one for 50 seconds. Then it's gone. You'd never see 3 at the same time. You could put them in geosynchronous orbit. Then they'd be so far away that you'd have trouble receiving the signal. They'd have to have much more power to reach you. And you'd lose some accuracy, too. So they put them in a medium Earth orbit. Put them up maybe 1,000 miles. Now, when that happens, it means the satellite is not whizzing over you. And it's not geostationary. It's somewhere in between. So if you have a GPS receiver, some of these receivers have little maps that show you which satellites are on the horizon. You can actually watch the satellite move. And it may be within your detection for an hour or so. They have enough satellites up there so that almost every place on Earth you can pick up at least 3 or 4 at any given time. But my car has this. It also has a built-in map. So it figures out where I am, then it displays the map showing me where I am. And it can do this to within a few feet. So GPS receivers now are being made a standard part of all cell phones. I don't know how do any people here have cell phones that they know are GPS? It's being done for just every cell phone, and the reason is actually a rather interesting one. It's so that in an emergency you can dial 911 and they'll know where you are. So you'll notice the GPS receiver does not send out a signal. A typical GPS receiver is solely a passive receiver. An interesting reason for that. Anybody here have a guess as to why? The GPS was designed so that it doesn't send a signal to the satellite, but it only receives the satellite. What's your guess? That's right. So other people couldn't know where you were. The GPS was designed originally for the military. It got its first big publicity boost in the first Gulf War when they had a few GPS receivers for our troops over in Iraq. And they were so valuable, the troops couldn't get enough of them. So they actually wrote home to the United States saying, would you go down to Radio Shack and buy me a GPS receiver and mail it to me? Now, these things were not mil-spec. They were not military specifications. But the soldiers quickly learned that the best way to avoid getting lost in Iraq was to have your own GPS receiver. So these things started going over there, being mailed by friends and family to the soldiers. So each one would have his own GPS receiver. It was a big scandal of the Iraqi War I that the U.S. military wasn't doing this. They weren't doing it because these weren't military spec. Military spec ones are terribly expensive. Military spec means, you can roll a tank over it and it still functions. These things probably have 50% chance of not working after a tank goes over them. At the same time, the value was so enormous that they basically changed the rules and started and let what's called off-the-shelf, commercial off-the-shelf. It's an interesting acronym, COTS. Everybody in the military knows this. Commercial off-the-shelf. So now we have a lot more like that. That's basically the satellite picture. We'll be talking a lot more about airplanes on Thursday. Don't forget to hand in your homework tonight. Oh, let me show you this before you go. This is kind of neat. I'm going to put a force on the card, but the force the card puts on the mass won't be enough to make it move. So the mass falls right down. I may set this up with some wine glasses next time.